Welcome to the video for chapter 5. First day, day 1, we're going to look at what's called an indefinite integral. And so basically, derivatives have inverse functions that undo them, just like the inverse of multiplying is dividing, the inverse of addition is subtraction. The inverse of a derivative is called an integral. And sometimes people actually call this integral is the actual noun. Sometimes people call it an antiderivative because it will undo a derivative. Now there's some notation for a derivative's antiderivative for the inverse, and it looks like this. In fact, you might think, oh my gosh, it looks a lot like the letter S. It really does look a lot like the letter S, and it looks like the letter S on purpose. We're going to learn more about its meaning as time goes on, but an integral is actually a summation, an accumulation. We're going to be taking a whole bunch of things, and the process of integration adds up a whole bunch of areas, which we'll see as we go on. You don't really need to know too much about this right now, but what will happen is if you have some function's derivative, let's say that we have some function f and its derivative is f prime. If you do the integral of that function, the integral and the derivative will undo each other and leaving you with f of x. Now, this is a little incomplete on purpose here. I'm going to come back to this in a moment. Let me add in one more thing. When we write integrals, you're going to see there's this thing at the end that'll say either dx or dy, and we call that a differential. And basically, it's notation that lets you know, first of all, that you're at the end of the integral expression, and second, it tells you what variable you're doing this with respect to. There are actually some other meanings to this that we'll explore later on, but for now, that will be sufficient. I am going to be putting something else here in a moment, so I'm going to come back to that. So work by yourself on this next one. Let's say you're told that y prime is equal to this expression 3x squared minus 7x plus 5. What is the antiderivative or the integral of that? In other words, what was the function y before its derivative was taken? So pause the video, try it, and look at your answer. Is your answer the only one that would work? Why or why not? And when you're ready, restart the video. All right, well, welcome back. Well, we know when we take a derivative that of a polynomial function that we use a power rule. So for example, if I have some function like this, if I took its derivative, I would take that power and I would multiply it and then to the coefficient that was already there, and then that power would be subtracted by 1. Now what we're doing is we are trying to start here and work backwards to this. Well, what we want to do is we want to recognize that that power used to be 1 higher than it is now. So I'm going to make that power, instead of a 2, I'm going to make it 3. And we also want to recognize that this number 3 in the front has that power multiplied by it. So I want to take this power out front and divide out the power of 3 from it. 3 divided by 3 is 1. Writing that 1, of course, is optional. For the next term, before I took the derivative, this must have been a power that was 1 higher. And this minus 7 has been multiplied by that new power, or by that original power of 2. I want to undo that multiplication, so I'm going to divide by it. This 5, at some point, must have been a 5x, because the derivative of 5x is 5. In fact, if you take the derivative of this expression using the power rule, you're going to get back to y prime. This is one possible answer. This is only one of many answers. Well, why? Well, maybe your answer had this. If you had a plus 2 at the end and you took the derivative of that, that would zero out in the derivative. Or maybe it was plus 36 or minus 14.2. But what we want to do is recognize that there could have been some constant at the end that would have a derivative of 0. The derivative of a constant is 0. And so we have no way of knowing what constant would have been there at the beginning. but we're going to put plus c to represent there was some constant there. That constant may have even been 0, but we don't know what it was. And so what we're doing is called an indefinite integral. The reason it's called indefinite is because we can't definitely for sure say what that original function was before we took its derivative. We are going to have to write this plus c at the end, and that's a capital C, to say, hey, we are not 100% sure what that constant was, but there would have been some constant there that zeroed out when we took the derivative. Remember, an antiderivative is also called an indefinite integral. The notation here, like an S shape, and then you'll have some function's derivative. This dx is telling you you're at the end of the integral expression, and the x is your input variable, and that is going to equal f of x plus c. Well, the first rule we're going to look at for this is the power rule. And the power rule is how we're going to undo derivatives. So if you are working with some expression like this, and you want to figure out what would the derivative of this expression have been before, if we're trying to undo that derivative, what would the original expression look like? What you'll do for the power rule is you're going to add 1 to the power, and then you're going to divide by that new power. And then there is a plus c at the end. Plus c. Now, in order to use the power rule, you do want all of your exponents to be written in ways that are understandable. In fact, if you preview a little bit and look ahead to number 3, just like when we do derivatives, we like to rewrite things in useful powers. That's going to be true in a question like number 3. All right, well, for number 2, I'm going to use the power rule. And when I use this power rule, I'm going to add 1 to the power, and then I will divide by that new power. Now, in a minute, I'm going to need to reduce that. You always need to simplify your expressions. And you can take the integral of multiple terms here, and you just continue adding and subtracting as you go. Well, I'm going to add 1 to the power and divide by that new power. 2 divided by 2 would make a 1. This would have had to be 3x. This is right now like 3x to the power of 0. I add 1 to the power to make it a power of 1 and divide. But I think it's almost easiest to think about what would have had a derivative of 3. Please do not forget, this is an indefinite integral. And so you must have the plus c at the end of the expression. All right, number 3. Before I can integrate number 3, it will be useful for me to take this expression and to rewrite it as x to the power of 1/2 plus 1/5, that's my coefficient, x to the power of -3, and then all of that's being inside the integral. I'm going to put the parentheses there to show that all of that's being integrated. The dx, remember, is indicating the end of the integral, and it's also telling us what our input variable is. And we'll find out more about that dx when we look at future lessons. All right, well, as I integrate this, I'm going to use the power rule. I'll add 1 to the power. Now, I want to divide by this power. Remember, when you divide by a fraction, you multiply by its reciprocal. Because you're dividing that's interesting handwriting. You are doing 1 divided by 3/2. Wow, the interesting handwriting continues. Yay, better. Plus, I'm going to add 1 to the power, and I'm going to divide by -2. Well, when you divide 1/5 by -2, first of all, there'll be a sign change, and it just puts that 2 on the denominator with the 5, and so that'll become -1/10. And do not forget the plus c. It's quite common for students to forget the plus c. And when Mr. Gannon and I grade your test, you get 1 point for the plus c. And you lose 1 point if you forget the plus c for every problem. So please make sure you remember it. Now you might notice that in these problems, number 1, I'm not factoring my solutions. That's because of the plus c. I don't know what that constant is, so factoring doesn't really make sense in this situation. I don't know what the greatest common factor is. It's also not useful. Derivatives factoring is very useful because knowing where a derivative equals 0 is something we use a lot. It's just doesn't really have applications in the integrals to factor this, so we won't waste your time. You might also notice that I have a negative power here. We have no problems with negative powers with integrals, so you can leave negative powers. With derivatives, it was more useful to not have the negative powers, but for integrals, you don't have to do the simplification. Let's take a look at number 4. We have one rule and one rule only right now. Our only rule is power rule. We don't have a quotient rule. We don't have a product rule. We don't have a chain rule. By the way, there are some implications for some of these that we'll get to later on, but at this point, all I know is power rule. So when I look at problems like 4 and 5, I need to rewrite them so that I can understand these problems better. All right, and I want to rewrite them by either expanding them out or actually doing the division that's indicated. And when you're talking about dividing by a monomial, each of the terms can then be divided by the monomial. So this could be rewritten as 5x squared over 2x, which can simplify, minus 4x over 2x, which can simplify, plus 8x cubed over 2x, which can simplify, all with respect to x. I'm going to keep my integral symbol there because I've not done any integration, but this would be 5 halves. And remember, when they have the same base, you can subtract the powers. So 5 halves x minus 2 plus 4x squared dx. Now, some of you are super bothered right now that this is not in descending order. Feel free to rearrange if you want. I'm not going to require that of you. I'm now going to use the power rule. Add 1 to the power and divide by the new power. I'd like you to notice when you divide by that power of 2, there is another 2 on that denominator. Minus 2x plus x to the third, right? I'm going to add 1 to the power and divide by the new power. You might notice I typically write that coefficient last. I should check just to see if any of this can reduce out. Remember, you do not need to factor, and negative powers are fine. All my fractions are simplified, and so I'm done with that problem. For number 5, what I'm going to do is I'm going to start by expanding this out. At this time, I don't have a way to handle undoing of like the chain rule. Now, as time goes on, we're going to have some different strategies, but right now, and even as we get other strategies, it's not really very useful to have things in this form. So I'm going to expand this out. 2x plus 1 quantity squared would be 4x squared plus 4x plus 1. I just FOILed it out. Make sure you multiply it by itself. And now I'm going to distribute the x. This is really 4x cubed plus 4x squared plus x dx. Notice I'm keeping my integral symbol here because I haven't done the integration yet. And now I'm going to use the power rule and do the integration. And as I do this, I'm no longer going to write the integral symbol. I'll add 1 to the power and divide by that power. Add 1 to the power, divide by the new power. Add 1 to the power and divide by the new power. Now, by the way, one way you could always check your work is you could go back and you could take the derivative of your answer and verify that it would get you back to the original integral. If you took the derivative of this and factored it, you'd eventually get back to the original expression. Remember, the derivative of c representing some constant, is 0. We are going to learn how to do the derivatives or the integrals of some trig functions right now. Not all. We will learn more of them as time goes on. But in AB, you won't learn everything you need to know about integrating trig functions. You'll learn a lot.